Can you hear me? I don't know if we have to use the mic or something. Can someone confirm if you can hear me or I don't know what is. Okay.
Yes, sir.
That is a new experiment for me also. Let's see how it goes. I hope you can see my board.
Yes, sir.
So yeah, this is the first hybrid lecture we are having. Only Atharva is in front of me, but if more people can join in the next lecture, that will be good. I plan to keep conducting in hybrid mode from today onwards. So every lecture will be offline plus online. So I think last time we started with functional equation. As such, because there are so many topics to cover, I cannot spend too much time on one topic. So I will have to move on to other topics. But I encourage you to spend more time with functional equations on your own. I think already the Vijay Venkatachara book which I mentioned last time, that is a good reference. And you must also be aware of this book, Arthur Angel's Problem Solving Strategies, right? So that is a good topic book for almost any Olympiad topic. So you can refer to those. So today we'll switch gears to a different topic, which is number theory. So in particular, I have to focus on diophantine equation. Okay? So I mean, pretty much all the examples which we will cover today are of the form, find the solutions of some equation, like integers or something like that. Okay? So I mean, just to keep a broad spectrum, I've chosen easy, medium, and difficult problems. So and this is also for your reference that depending on every student's difficulty level, right? You may want to refer to three possible sources for problems like this. So first is RMO problem. So this is particularly for those who are not attempting INMO this time, but will be preparing for IOQM for next year. So those students can attempt RMO problems as one reference. Then the next is of course INMO past papers, and the other is IMO shortlist. So obviously IMO shortlist means the problems which have been shortlisted to select in International Maths Olympiad. So they are going to be difficult, but if you know anything about how the shortlist is organized, each subject is organized from easy to hard. So for example, for number theory, you have problems N1, N2 up to N7. So typically the first two, like N1 and N2 of every year, that is something that you can attempt as an INMO practice. And same goes for all the subjects, so algebra, geometrics. Okay. So in that respect, I have decided let's do two problems of each difficulty. Okay. So two from RMO, two from INMO, and two from shortlist. So I'll write the problems on the board, but to begin with, let me just write the problem numbers. आवाज येतो का ऑनलाईन याच्यामध्ये ऑनलाईन नाही थोडा येतो आतापर्यंत वापरताना केवढा येतो Okay, so these six problems you would like to do. So I'll write the problem statement also, but we can get started if you already have the question paper with you. So as I already said that all questions are the type find integer solutions. So I would write the full sentence every time. I'll just mention the domain and the equation. So Question 6 is a functional equation actually in numbers. And the part number 3, part number equation. Can look at the first question or some more time. So this kind of question goes back to the idea which we keep on finding in number theory problems, which is estimation. Okay. So if you look at this clearly, y will be greater than x, right? Because y cube is equal to x cube plus some quantity. Of course, there is a term minus term here, but you can clearly see that 8x square will be greater than 6x. So on the whole, RHS is definitely greater than x cube. And therefore, basically y cube is greater than x cube. That's y will be greater than x. So, but you look at the expression, and it seems like y cannot go very far from x, because sooner or later these terms are very small compared to x cube, right? So y cannot be very large quantity compared to x. And very roughly speaking, you see this is looking like some kind of x plus something whole bracket cube expansion kind of expression. So that is the motivation to try to compare what can y be with respect to next few consecutive cubes after x. So obviously x cube is there, but if you look at the next few terms, right, x plus 1 cube, x plus 2 cube, and just try to get a sense of, like, just try to estimate that whether y can be accommodated in any of these ranges. At some point, you'll be adding a constant which is so big that that expression is clearly greater than y. So that means that we have bounded the upper limit of y. Okay, so that is the first sort of intuitive observation. Even before you start, the calculation details are the next step. But before you go into the details, just think about this strategy, that how you can estimate the relative magnitude of y and x. So that is the first observation that you can start with. And the only reason this approach will be useful is because x and y are given to be natural numbers. So once you have bounded the upper limit of y, then trial and error can finish the problem. So does anybody already have some solutions? Like, did you find any solutions of x y which satisfy?
X equal to 0 and y equal to 2.
But x y are natural numbers, right? So I don't know if 0 is allowed. I think if I copied the question correctly, we have to take positive x y. But anyway, can you tell me the solution again? X equal to 0 and
Y equal to 2.
y equal to 0. Yeah, that looks like a solution. So if you just write the first two terms of x plus 1 cube, etc., what do we see? So x plus 1 cube is So as soon as you write x plus 3 cube, right? Up till that point, we cannot be really sure which is larger, which is smaller. But now, here every term is greater than the RHS. So we can clearly say that this is greater than RHS. Correct? And RHS which is equal to LHS is y. So in other words, x plus 3 whole cube is guaranteed to be greater than y cube. Which means that y is now forced between x and x plus 3. Okay, is everybody following this? How we are forcing the possible values of y between two natural numbers, and in fact, there are only two possible values that we need to consider. Right? Either y is x plus 1 or y is x plus 2. So again, the details are not important, the strategy is important. How do you arrive at this idea? In fact, one more idea I'm thinking now, I don't know if it will work out, but looking at this, right? First solution 0 and 2, and there is this 8 which is sitting there, which is obviously 2 cubes. So it would be a tempting idea to just separate out x plus 2 bracket cube from the expression and just write this as x plus 2 bracket cube plus whatever is the remaining quantity. And I don't know if that could lead to one more solution. We can think about that.
Nine and 11 are not solution.
9 and
For x is for the for x plus 2.
okay. And for x plus 1, so for x plus 2, that is the only solution.
Because it's
Oh.
for x plus 1 there is no solution.
Okay. So let's start analyzing the two cases. So let's case 1 y equal to x plus 2. So in other words, x plus 2 bracket cube is equal to our expression, right? Calculate correctly, or is it the-
8x square minus 6.
So expanding, yeah. So basically 8 will cancel and one copy of x will also cancel, right? So we'll be left with so now this is simply a quadratic in x. Or no, not even a quadratic, right? It is one.
X plus 12. LHS. X square plus 6x plus 6.
So in fact, it's not even a quadratic because x will also go away. But this is simply linear and we will get 2x. X is 9. Okay, so this is the only solution in this case. And in the other case, if y is equal to x plus 1, then we get. So I think this time we'll get a quadratic, but quite possibly the discriminant is not the quadratic. That's what that. Happens. So yeah, and I'm giving the calculations to you, but no solution is presumably. And I mean, if the x y are allowed to be non-negative, then even 0,2 is a solution. But we don't have to consider that. Actually, if x y are allowed to be negative, then we have to be a bit more careful.
Because you can't cancel that x.
Not only that, but the whole estimation idea was resting on the fact that x plus y, x plus 3 whole cube was greater than y cube. If some terms are negative, then we have to be more careful whether how we can compare the terms. So the fact that x y given positive was a very good blessing for us. So in fact, then that's the next generalization you can think of, that what happens if I don't restrict the domain to just positive integers, but allow negative integers also. So then how we have to modify our strategy? That is something we need to think about. But in general, yeah, I don't know, we cannot say for sure. I was going to say that two cubics cannot intersect in more than 3 points, but this is not, we have two variables, so x and y can be independently changed. So just because in positive side we got finite different solution doesn't mean that in the negative side also we necessarily get finite solution. So I think we have to think about the negative problem independently. Okay, so give that a try. So that's one thing, that when you solve one problem, don't just stop there. See how much you can generalize it, how much you can push it, because that will also tell you what are the limits of each tool. Like for example, here itself we saw that estimation is a very good tool if the numbers are positive. If the numbers are negative, I think still you can do estimation, but it is like we have to be much more cautious about that. These details are important. Okay, so going back to the problem. So that was question one. A very typical like RMO difficulty question, I would say. And this is something you can expect at IOPM also. And honestly, the way IOPM difficulty is, this is simple for IOPM also. But anyway, so maybe question two. So as I know we are solving the questions, keep track of what are the problem solving techniques that you are encountering. So like estimation is one important idea we saw just now. So several such ideas that we are going to encounter. The same problem will never repeat in Olympiad, but the same themes or ideas will repeat, right? So that is what we need to spot. This is what we know.
When vertical equation ratio minus 3 equals F2 times F2
Okay.
So one call is the solution. Okay. About A and B, then A is equal to minus 2. And now we will do it. How to do that?
So first idea of this we can think out is try to eliminate n from both equations, right? So that we get the equation purely in terms of A and B. So we can try that. So just substituting n equal to a cube minus 3
Sir, I have another idea.
Yes, tell me.
So what if we multiply the first equation by m? So we won't get a perfect cube, right?
If we multiply this by m,
We'll be able to eliminate m square and 3m both.
yes, but we still will have one copy of m remaining, right? Because this will be m square plus 3m equal to m times a cube, right?
Yeah, m times a cube minus b cube.
Which is m, a, and b, all three. Which is fine, but I mean, as far as possible, if you want to eliminate m, you should eliminate m completely, right? Otherwise, we are probably increasing our complexity instead of reducing it. So actually, there is a similar approach in my mind also, but I'll talk about that later. First, I want to see what happens by just substituting m and whether that gives us anything useful or not. So n equal to 18 minus 3, so we'll get 8.
So we get the same thing in both ways.
Okay.
So the a cube minus 3 into a cube is b cube minus 3.
When we eliminate m by what Anushka said.
Yes, even there we can substitute that m is equal to a cube minus.
Oh, yes, yes, correct. Yeah, so there also n can be replaced by 18 minus 2, correct. And maybe that is easier to calculate then.
Yes.
Okay, then we can go by that. So then, as what Anushka you are saying, let's write m square plus 3m is equal to 8 cube into m. And so therefore, we can write this as 8 cube into m plus 3 is equal to 3 cube. And now to get rid of m, we do the substitution only here. Okay, that's actually easier to calculate than substituting m here. So we get 8 cube times.
So what do you do in this last step?
Here I'm substituting this m equal to a cube minus 3 to get rid of the m, right?
Okay.
Now we have the a and b in our equation, which is easier to handle.
Okay. Okay.
So in fact, this problem also has a very similar flavor to the previous problem in some sense. Only slight complication is that a, b are integers now, so we have to be more careful about the estimate. But notice that I can write this in a little bit different way because see, a raised to 6 is the dominant term on the left hand side, which is also perfect cube. So in a way, we are saying that there are two perfect cubes which are very close to each other in some sense. That's what we are saying here. But we need to formalize that in some way. So let's see if we can do that. One more way to think about this estimation is, see, we know m plus 3 is a perfect cube. Using that, can we find one more perfect cube which is close to our expression? Whole square, right? So m plus 3 whole square, which is m square plus 6m plus 9, is also perfect cube. So if you just compare this expression again, you get a similar flavor to what we were doing previously, that we have two perfect cubes which look very similar to each other because the dominant term is the same. So just the difference of 3m plus 6 is there between two perfect cubes. So again, the distance between b and a square will be bounded in some way. That is the intuition that we get from this. Okay. But which will follow, which will largely depend on whether m is positive or negative. So if we probably can make cases that let m be positive or m be negative, so that we can handle this in me. So let's assume that m is positive. Let's say we are talking about m greater than 0. So then clearly this is greater than this. So, but it cannot be very far away. That is our intuition. So how do you write the expression to sort of crystallize that idea that how far can this term be from this.
So as you increase, and the difference will increase.
As you increase m, the difference will increase. That's correct. But I mean, if you just think about it, the distances between cubes are quite large because cube grows very fast, right? So this is the perfect cube. The next perfect cube will not occur very close to that. So how do we capture that idea? So let's try this maybe. So a square is going to be greater than b. So which means that b will be a square minus something, right? Presumably. So we can try to look at similarly what we did before. Let's try to look at a few perfect cubes before a square. So a square minus one perfect cube. So how much will that be? And sort of try and compare this expression with what we get from b.
B cube is a raised to 6 minus 3a cube plus 3.
B. Can you repeat that? B cube is equal to
A raised to 6 minus 3a cube plus 3.
So if I compare this expression, can you say that which will be larger and smaller? If we can make that kind of estimation, that will be useful for us. So top item to see this is obviously equal. So and we can ignore the constants for now. So just focus on the part in the middle. So minus 3 raised to 4 plus 3 square and this part. And by the way, why am I saying ignore the constant? Because maybe for some small values of a, the constants will make a difference in terms of flipping the inequality. But once a is sufficiently large, the constants are not going to be the critical point. So it's okay to ignore them at least for now. When you write the proper framework, you have to be more careful. But to arrive at an inclusion, just compare these quantities and see if we can estimate which is larger or smaller. So in a way, this is minus 3 raised to 4, which is a very big negative quantity. So this will be larger than this in the negative sense. But then there's a plus 3 square also, which will sort of increase the value of this expression somewhat. So, but with some rearrangement, can you see how which one will be larger as well? I think by this side.
With the lower order will be larger.
This will be larger.
Yeah. So we can just take minus 3a.
Yeah, we can minus 3 square, but can be cancelled from it, right? So I'm comparing this versus minus 3. And we can cancel 3a square from both sides, and 3a square is always going to be non-negative, so it will not flip the sign. So what will be left with this minus a square plus a versus cancel 3a square, right?
A.
Minus.
Yes.
So I think here we can let me see minus a square is going to grow much faster in the negative side than this. So we'll be like this. So this is our intuition that this will be greater than this. So then we are almost done, right? Because what you are saying is that a square minus 1 bracket cube is less than b. And b, from this we know that b is less than a square. So this is less than A square.
Then B is greater than.
So basically, B will have to be equal to this, and it will be greater than or equal to kind of. Because there is no perspective between these two cubes.
Or else it equals there. Because B is equal to A square.
Yeah, that's it. So yeah, B has to be either equal to this one or this one. So now we get the overall picture that this is how the solution can work out. But now, because we ignored the constants and we did some like rough guesswork, so we need to formalize everything. But I hope the idea is clear that how we are again using estimation to get the initial sense. And of course, all of this is for n greater than 0. I don't know if that matters also. Yeah, that matters because otherwise we cannot write this. So we'll come to the n negative case after this. Okay, so if we try to write everything more formally, let's try that. So again, we are talking about case 1. Greater than 0. Therefore, what we will say is that a so because I want to compare the two, I'm just subtracting the two expressions. And because we want to finally show that B is track between these two conditions. So I'm interested in B be greater than S.
Isn't it B cube is equal to A raised to 6 minus A?
Oh yes, sir. So that's why I subtracted that two, and now my goal is to show that this is non-negative, right? So now, as we what we did before, we can group these terms together and we can write this. And for this quadratic, I think we can see that the roots are basically after a greater than 1. for all the greater than 1, this will be positive, non-negative. So that means that we just need to consider the case when A can be 1 of the separately, but for in the most general case, this is always going to be greater than or equal to 0. Therefore, what we can say is that B is either A square or A square minus. And in fact, I don't know why we are calling this strict inequalities. I see that there is no, because if you are taking m greater than 0 strictly, which means that this is strictly greater than this. So this is a strict inequality. And if A is greater than 1 also, then this is also strict inequality, right? So it means that there cannot be any solution. Correct? Only in case where we are assuming A greater than 1, what will happen if A is less than 1? Can that happen? I forgot.
M is greater than 0, then A will be greater than 1.
Yeah, I forgot what was A. A was
A is A cube is M plus 3.
A cube is n plus 2. Yeah, so if m is greater than 0, then clearly A cube is greater than, in fact, A is greater than 4. So then therefore A cannot be less than 4. Okay, fine. Okay, so looks like in this case we are not getting any solution at all. And I even tried to substitute a few small values, but I did not find any solution. So I think this is the right one. So this was about m greater than 0. If m less than 0, what will happen? I mean, how will we have to modify our strategy? Before that, any doubts in what we did here? I mean, understand both. This was what you will probably write in the exam in the fair part, but before we did that, we also did the rough estimation. That is the important part.
So can you re-explain this case? I don't understand.
Sure. So we are assuming m greater than 0. And so, I mean, firstly, I hope from the previous work you understood how we got these three equations. So B A square and this one. So these are our starting points. And so now this term being greater than the 6m plus 10 being greater than 3m plus 3, we can say that A square whole cube is greater than 3. Which means that A square is strictly greater than 3, not even greater than equal to. Also, so we have got a sort of upper bound for B. So B will be smaller than A square, but we have to see how much smaller. So the next perfect cube before A square cube is A square minus 1 whole cube. So we wrote that. And our objective is to show that B is greater than A square minus 1. So B greater than A square minus 1 means B cube has to be greater than A square minus 1 whole cube. So therefore we are subtracting B cube minus A square minus 1 whole cube. And we expand that and simplify it. And then what we are left with is this quadratic in A square in A plus 4. And because we are considering the case m greater than 0, so A cube is equal to m plus 3, which means that A is not very small, particularly because this will be at least 4. So A cube is at least 4. So I think A is going to be definitely greater than 1. And then you can check that this quadratic equation will be positive for all A greater than 1. No, sorry. Greater than equal to 2 actually. I mean,
A is greater than equal to 2.
yeah, because they are different integers, so we can say that. Okay. So A greater than equal to 2. So therefore, we can be sure that this whole quantity is strictly greater than 0. In other words, what that means is that B cube is greater than A square minus 1 cube, or B is greater than A square minus 1. And therefore, basically B is trapped between two natural numbers, A square and A square minus 1, and that cannot happen. Okay.
Okay, sir, got it.
Don't get any solution in this case. Now, m less than m equal to 0 case, obviously we can just substitute and see that that cannot happen. So now the next case is m less than 0. So obviously we'll write everything afresh, but just to see where in this strategy we have to make suitable modification. So first thing is because m is less than 0, this comparison is not so clear cut. That because now 6m will be more negative than 3m. So term by term, in fact, it is going to be the reverse. 6m is smaller than 3m, but 9 is greater than 3. So then the relative magnitude of m matches. But again, this is where we can first the intuition can be developed by ignoring the constant, because once you take m sufficiently large, this difference 9 minus 3 will be overcome by the 6m and 3m, right? So broadly speaking, we can see the picture that is this time the sign will be flipped. So it will be d less than a square. Oh no, sorry. I mean, sorry. B greater than a square. Okay, so the magnitude will be reversed now, and we have to take that into account when we write the next expression. So
Sir, but then in case of very small numbers, like it may not happen, right? Oh, sorry, very large negative numbers, the magnitude is small.
for very large negative numbers, again, like the intuition is that we won't have any solutions, right? But yeah, we need to verify that somehow.
So what we can otherwise do is that we equate 6% and 6% and 10%, we get -2. So you can just make two cases, n is between -2 and 0, and m is between -2 to
No, but why are we allowed to equate that?
like in the rough form we can
In
equate
the, yes, correct.
okay, so we can analyze them.
Yeah.
And we can
Yeah. So I mean, if we make the guess that maybe b and a square are equal, in this case, the both expressions will be equal, right? So then we can just compare and get an estimate of how big or small m can be. And then we don't have to check for values outside of that, at least to find the solution. Let's try that actually.
So for m is equal to 2, we get this m is equal to -2, that works.
Okay,
So then we can just see what happens in -2 to 0 and -2 to -2.
right. Okay, so m equal to -2 is the solution. Okay. So now we are considering the case that m is less than 0. So, so now intuitively, because we think that in the most general case, like if m is sufficiently small, then we will have 3m will be less than 16, right? So basically, we will have the condition that b is greater than x. So we have to look for the next few cubes after x square. So that's why I'm now writing x square plus 1 bracket instead of going the negative direction. So we are going to get a raised to 6. And again, same as before, we have the expression about this one, right? B6 equal to a raised to 6 minus 3 plus 3. So again, we have to compare the magnitudes of this expression with this one. But now bearing in mind that n is negative, so quite possibly a is also negative. Note that a will be negative, but b will still be positive, right? Because m square plus 3m plus 3 will be positive. Like for again sufficiently small value of m.
So even a can be positive.
A can also
But again we get to that -2 because
see a can be both positive or negative. We cannot-
if m is between -2 to 0, then a is positive,
Right.
otherwise a is.
Right. So now our hope is that we want to capture b between a square and a square plus 1. So we are interested in comparing the magnitude of a square plus 1 and b. So we can write a square plus 1 minus b cube will be equal to this minus. So now to subtract. And this will get very similar calculations to the previous one. Because again, the same thing will happen, right? Here is so again, do you see that sooner or later this term will be the dominant one? And so for sufficiently small or large value of a, this whole thing will be greater than 0. So the only sort of case where I guess we will actually get a solution is when so if you notice this, we assume b greater than a square only if this term dominates this. So basically 3m plus 3 being greater than 6n plus 9 led to this whole calculation. So if we assume that that is not the case, in other words, what we are saying 3m is 3m compared to 6, so which is n equal to 9. Second question. So n equal to minus 2 is already the solution that we found, and so for all n less than minus 2. So therefore, as what Arnav said, that let's make the assumption that n is less than minus 2, so that we can safely say b is greater than a square, and from this expression now b is also less than a square plus 1. So again, b is tracked between two consecutive natural numbers, right? So on the whole, n equal to minus 2 is the only solution, both positive or negative. Okay. So this is one more problem where estimation is playing a very important role in the whole. In fact, I was thinking whether divisibility kind of argument can also give us something useful, but I don't know what to think about that.
Sir, what about -1?
Minus 1, so you can just substitute and check, right? If m equal to -1, then n plus 3 is not a perfect cube. So that's the end of that. So
Okay.
if you bounded f between some small number of ranges, then just trial and error can finish the problem, right?
Sir, I used another approach.
Yes, will be.
We know that m plus 3 is a perfect cube and m square plus 3m plus 3 is also perfect cube. So m plus 3 into m square plus 3m plus 3 is also perfect cube.
Yes, correct.
If m is equal to -3, not necessarily the second bracket is a perfect cube. So in fact, if we substitute, we don't get it to be a perfect cube. So m is not equal to -3. So after that, if we manipulate it, we get that m plus 2 whole cube plus 1 is equal to some n cube.
Oh, interesting.
And difference of two cubes is 1. So it's either 0,1 or -1,0.
Interesting. Yeah, once we look at this, it's clear that we are talking about two consecutive cubes. So again, very finite number of cases to be checked for that.
But with -1,0, we get that m is equal to -3, which is not true. So we take the case of 0,1. So we get m is equal to -2.
Right. Yeah. Yeah, and basically there are only -1, 0 and 0, 1 are the only two pairs of consecutive cubes. But this is interesting that we sort of multiplying these together. And now I'm remembering, when I saw the official solution, I think this is what they also did. So when you expand this, you are getting m plus 2 bracket cube plus 1. That is interesting. Of course, the question is that how are you supposed to think of this idea? But it is natural in some way. I would say that when you are given two cubes, basically the idea is can you generate more cubes out of that? So obviously multiplying two perfect cubes will also give you a perfect. See if there is any other justification of how we can think of this idea, because that is quite important. But what is the every question always has some clue or some hint in that which suggests you that this is what we should try to do. So yeah, every question always has some hint or clue which should suggest you that this is the approach we should try. So what was the hint or clue? So Janu, why did you think of multiplying them? Was there any reason or you just
Observe that 3 into 3 is 9 and 2 cube is 8. So if by guesswork I just identified that this is m plus 2 cube plus 1.
right? Yeah, I mean guesswork can also be very powerful sometimes. That's a perfectly valid approach. So see, as and how we encounter these tricks, we should keep adding them to our toolkit. That next time you encounter a problem about cubes and something like that, you should sort of your brain should go back to this problem. That okay, that's what we had done then. So let's try applying it here now. So we need to grow your collection of techniques like that. So obviously you cannot remember every problem that you solved in the exam, but try to remember at least the strategies or things for that. And for that, what is important is to start documenting what you can call a toolkit, right? So 1 page or 2 page summary of all the important ideas. So estimation, like whatever other trick you are learning here, divisibility, congruences. So try to document those important techniques to make your revision faster, basically. Okay, but I think we move on to the next problem.
Actually, your previous method, I would think that instead of m greater than 0, we can just say m greater than -2. Because
Okay.
we also make another -2, so we just want to make two different cases in m less than 0.
Okay.
You can just take greater than -2 and less than 2.
Okay, so when we, in case one, if we just take m equal to minus greater than -2.
So the square is greater than
Okay, I see. So this part is, I think I get that part, but yeah, basically we can still say this. Yeah, so once you get the -2 solution, then becomes clear that that is the place where your part is. Right. Okay. Yeah, in fact, that's just one important thing that probably before starting to attack the problem, we should have tried small groups. So once we arrive at the -2 solution, it adds some clarity to our approach. There's something to keep in mind. Okay, so moving to the next problem. This was question 2. So now, so we'll look at question 3 and 4. Starting with question 3. So these were the first two were RMO problems. So these were more relevant to those who are going to try for IOQ. Then the IMO problems, again kind of similar flavor, but just see how you are approaching them. So observe how your problem solving toolkit also changes as the difficulty changes.
So, how do we start focusing this?
There is some kind of factorization is being hinted at, right? Because both sides are having the same factors. We can probably write this as x plus y times. So if x plus y is non-zero, then we can cancel this and so I guess we have to make two cases that x plus y non-zero and x plus y is plus y is zero, then what will happen? Basically, z is supposed to be 1.
Then you get a combination results.
Right. Yeah, because any x and its negative will work.
Yes, we come minus
Like, I can do it. So for all integers, we get one infinite factor, and this is the only factor possible in x plus y. So now we can safely assume that x plus y is not available. So in that case, cancelling x plus y and 1 minus z. So we get x square minus. So now effectively we can ignore this equation because we have converted that information into this and just work with this equation and x plus y equal to 1 minus z. And even this we can eliminate z. So we will get an equation in only x and y, right? So we have x square minus xy plus y square plus x plus y. This is a pair of lines. So this is a second degree equation in two variables. And if somebody knows some theory from 11th or 12th standard, then the phonics are kind of implied here. Obviously, I'm not saying that we have to use that here, but just to build an intuition, how can we leverage this? And I'm somehow thinking of comparing this to first take everything on one side and imagine that this is a product of two lines. So line is obviously a plus by plus c type of equation. So what happens if I multiply two lines like this? So actually there is a standard formula to check whether the coefficients of the equation match this formula. That may not always happen, but just looking at the equation, it seems very tempting. Okay, otherwise, see, xy term were not there, this is the circle, because x square, y square, xy, but the xy term means that it is not a circle. So then what is it? It can be like some rotated ellipse or hyperbola, maybe, I don't know. Yeah, but anyway, I mean, keeping that aside, what else can we do? Some kind of completing the square is also one possible idea. It seems to be the case, right? Because there are a lot of cross terms there. Right?
So I ordered it was x plus y whole square plus x plus y is equal to 2 plus 3x.
Okay.
So, but I don't know.
So x plus y whole square. So basically you try to complete the square for this, so we get 3x square. I guess that's a useful approach. So what one more thing you notice is that this is symmetric in terms of xy, right? So whenever you have symmetric equation, it's always good to think in terms of the elementary symmetric polynomial. So x plus y and xy. So in fact, let us call them x plus y as the sum, and xy as the product. So we can change the variables from xy to s and p. Although there is a slight risk there in that. See, generally when we change variables, we want to make sure that we have maximum degree of freedom. Here we are not free to choose any value of s and p, right? There are some restrictions on which s and p.
X and Y integers.
Exactly. And of course, because of the quadratic thing, you have equal variables. So for x and y to be real numbers of your spherical and 4p is of course one condition, but that's not the only thing. I mean, s square minus 4p in fact has to be a perfect square in order for x and y to be even rational numbers. So that is one extra constraint we have to consider. But just it will make the expression very nice. So for that reason, I am thinking let's try that. Let's see what happens. So what do you
X
get?
square plus S is 3 plus 2.
X plus y square becomes 3x. So this is what we get.
Plus X plus 1 in the non-existence.
So s square plus f 3 plus. Let's see if we can use it. But the fact that s square minus 4p has to be a perfect square and a square. Some of this looks very close to each other. So can we
The one thing we get that S is common to one more.
s is common to one more? Okay. Yeah, because basically this is s into s plus 1. So the product of two consecutive numbers and RHS being 0 or 2 mod 3. So that is the only problem. So whenever we get something like that, it's useful to replace s with 3s1 plus 1 and see if that helps us. We can try that, but before that, again, just try to see if some estimation idea can be relevant here. One more approach can be, so we will think about this, but just going back to this expression, there is one more thing that looks very close to this, which is x plus y plus something whole square. So consider some x plus we have to see bracket square, and because there also you get like xy cross term, pure x square, pure x. So this same kind of form will be coming out of this kind of expansion form. So try comparing that.
It won't be directly C square.
It won't be directly, but can we see how can we minimize the difference in some way or something like that? Okay, so let's think about, so to make this work, you need 2 everywhere, right? So let's multiply our equation by 2 and see what we get. So we get Now, how can we do this?
Sir, if we multiply the equation by 4, we get 2x minus 1 y plus 1 whole square plus 3 times y plus 1 whole square is equal to 12.
Oh, okay, that seems interesting. So, okay. Right, so we'll get 4x square minus 3xy plus 4y square. And now here the way you are splitting, so 4x square will become 2x plus something. So see the intuition here, first attempt what we'll do is we'll try to put 4y in the same page. But what you are suggesting is something different, right? So I think you are splitting this as y square and 3y square, right? Something like that. From
Yes,
top,
sir.
yes,
Sir, it should be minus 8.
minus 8. So basically, if we consider 2x minus y and some constant square, we have to work out what that constant will be. And plus, so because 3y square will be 3 times get y plus some constant square, and then some constant will remain. So this kind of expression is what we suggesting.
Yes, sir.
What should be the constant to make this work? Can you work that out? So for example, we want 4x here, right? So 4x will come in, we have plus 1, right? Plus 1, and here we will require. So this is minus 4y can be written as again minus 2y.
Square plus
Minus 2y.
minus 2y.
Yeah, can you repeat your final expression? Shreyas, right? Shreyas.
2x minus y plus 1 whole square plus
Actually, it's 4x plus 4.
Oh, okay, that. Then we plus, okay, then it will work out, right? So now we have 3y square and plus 6y, so it will be y square plus. 3 times y plus 1 whole square, something like that.
yes, sir.
And then the remaining constant is coming out to be 9 and
Sir, it is equal to 12.
okay, so this is very nice. So now what we are saying is that sum of two perfect square is a constant. So that puts a natural upper bound on these values.
Perfect currency times.
Perfect square and 3 times. But I mean, just directly also considering that the magnitude of this. Yes, correct. So now we just have to try the values of this whole thing will be less than equal to. No. Basically, these individual expressions now cannot be greater than 3. So when this can be at most 3 and minus 3. And the same for this one. That's still a lot of trial and error actually. But still it is
So
manageable.
actually, we can try 2x minus y plus 1 whole square as 1, 4, and 9.
Yes.
So 1 does not work, 4 does not work.
Okay.
Because the
Zero, yeah,
zero.
okay, yeah, we can do that. So basically because this is perfect square, only possible values we should consider are 0, 1, 4, 9.
And even 9 will work.
So 0 works because 0 and 2 is a valid pair. 1 does not work. 9 works. 9 and 1. So yeah, 0, 2 and 9 and of course plus minus. I mean not this is not plus minus. But when we take the square root, we have to consider both roots. So 2x minus y can be 0 and y plus 1 can be 2. Y plus 1 can be plus 2 or minus 2. So both cases have to be considered separately. And in the second case, 2x minus y plus 1 can be plus 3 or minus 3 and y plus 1
So y plus one is plus one or minus one, right?
Yes. Yeah, now we can just work it out case by case and we'll get the answer. So, I mean, the rest of the details are not important. But yeah, this was actually an important step that how do you convert the given expression into a this kind of a sum of two square. That was the trick there. And I think this is where some geometric intuition will be useful. So now just look at this expression and think of it what there is being in the 2D coordinate plane. That some this quantity square plus another quantity square is a constant. So have we encountered this? Actually, we have not done the radical axis and those things before, but I done that in the last year's course. But intuitively try to get a understanding of what is the meaning of this expression in terms of, because there is obviously ignoring the integer part. This will describe some curve or surface on the in the plane, right? So what is the shape of that going to look like?
Circle.
See, because the xy term, that it won't be a circle exactly. It's going to be an ellipse of some kind. What I the way we can make sense of this equation. So look at this part. This is a straight line. This is also a straight line, right? And this is y equal to minus one straight line. So in the coordinate plane, y equal to minus one. So this is this line y plus one equal to 0 line. And 2x minus y plus 1 is also going to be the line. So which will pass through where x equal to 0. I get y minus 1. So in fact it is a line passing through this point, right? And it's a positive slope line. So if I set y equal to 0.
But it will pass through one, not minus one.
It will pass through 1. Oh, sorry, it will pass through 1. And it will pass through, I think, minus 1. So these two lines at any point P. So we are talking about this distance. Now note that these expressions are nothing but distances with some constant in the picture. Because in the general expression, the distance of a point, if you have a line x plus by equal to c, or x plus y plus c equal to 0, and some point x naught comma y naught, then the expression of the distance of that point from that line is just substituting x naught y naught into that expression and divide by x plus b square root. So in that sense, this is just the distance of the point from the two lines. So PA square, some into some constant plus beta times dB square is itself constant. So that is the kind of expression. Okay. And if those constants were equal or 1, then this would be like a circle. No, not.
Yeah, the lines. Yeah.
But yeah, that kind of geometric intuition could be helpful.
But why would it be a circle in the xy term dimension?
No, actually, the way I'm looking at it, basically, I'm looking at a new coordinate frame. So, this, if I consider these are the fundamental coordinates, in that frame, it will be a circle, and so in our plane, it will be an ellipse, something like that. Because basically, you can think of these as distances from the axis. No, not necessarily, because this is not a parallelogram. Okay. Anyway, I don't know. Basically, what I'm trying to see is that how are you supposed to think of a step like this? Right? From the previous expression, why would you think of suddenly jumping and setting those constants? It particularly like splitting y square, like when we got 4y square, again the first intuition is to group this together, but splitting that as y square and 3y square, that was the step.
I think maybe because we require the minus 2xy term.
Minus 2xy, right?
Minus
Minus 4xy. Yeah, because here we are getting 2x whole square. And that will get multiplied by 2 because of the cross term. So we will give only one copy of pi, something like that. Yeah. So yeah, anyway, I mean, this is a valid solution, but I feel that many times it's not a very instructive solution because it doesn't help us in the exam. Like how are you supposed to think of this idea? That's why I'm also trying to work out with this approach, like a much more natural approach, like converting from x y like frame of reference into s and p, and to see if that can be evaluated. So maybe we'll move on to the next problem, but keep thinking on this idea also that how can you approach a question like this naturally? As far as possible, we would like to find more solutions of this kind and less solutions of this kind. And actually, I know for a fact that this is exactly how the official solution is also. So see, that's the problem. The official solution, they say consider something expression. But why should you consider that? That is not there. So that is the problem. But see, you are getting a flavor of how these problems are that some clever trick or manipulation is the what you need to find out. And the more you practice these kind of questions, the more these ideas will occur to you. So I'll leave this as a sort of exercise for us to see if this approach can be completed S and T, but we will move on to the next problem for now. Yeah, we didn't actually find the solution set, but that's okay. I think we can complete that on our own. So, going back to the question. Okay, question 4.
All those solutions that I saw in-
Then we can move to the next question.
That was in one TV plus two, no? So, yes.
Just to return to the previous problem, looks like that other approach is also workable. So let's quickly look at that. I hope that will lead to the same solution. So SQL process is going to be. So this is the starting point for us. SQL plus S dt plus 2. And in general, if S and P are any real or X and Y can be any real number, then the only criteria is that S greater than 4P. That the discriminant is positive, but in addition, because they are talking about integers, so not only is the discriminant positive, but it's a perfect square. So square minus 4P is a perfect square. That something you can try to use. Now, as what you noted that from here, basically modulo 3 gives us that S is going to be one more. Right? So let's say S is equal to 3 times S1 plus 1, and we substitute that and see what we get. So we'll get 3 times S1 plus 1 times 3 times S1. So then simplifying what will be get. So we will cancel and line. Basically we'll be left with 3S1 square plus 3 times S1 is equal to P. Okay. That is what will be left. No. Yes. And now the same thing we can do here also. Right? Here S can be replaced by 3S1 plus 1. So we'll get 3S1. I don't even know whether I need K square here, but I'm not sure. I think enough to consider greater than equal to 0. So we are going to get, and now the fact that P can be completely replaced by this expression. So we can get everything in one variable, right? So here if I just substitute P over here, what will I get? So I'm basically going to get a quadratic in this one. And now if you just look at the coefficient of the leading term, right? This is 9 and minus 2. So it is going to be basically minus 3S1 square plus something, doesn't matter, is greater than equal to 0. And now if you see this minus 3 times anything, this is a inverted parabola, right? Yes. So basically there is only going to be a finite domain in which this will be valid. So basically you have restricted the number of possible values of S1 now. Yes. To some finite range. And then again, I don't know whether we have to do some trial and error after that, but at least we can control the problem to some extent. That is what I observed. So anyway, I'll leave you at this point, but see if you can complete this approach. And if you can complete this approach, that is a much more instructive sort of analysis that you can think of this idea in a different problem. Okay, so everybody understood the overall strategy of how we are proceeding. See, anytime you get this kind of common answer, it's a good thing to substitute and simplify. Sometimes it is doesn't lead to anything new, but many cases it will simplify things for us. This 2 getting cancelled, 3 getting cancelled. So generally it's a sign of progression that whenever we are able to do this. In fact, this is the same way in which if you remember how Pythagoras general formula for Pythagorean triplets evolved. It also involves multiple substitutions like that. So, okay, so let's note this and we'll return to the next problem. Okay, so let's start thinking on the next problem. So unfortunately, I have to cut short today's lecture by some time. I have to leave at 11:30. But let me just highlight the approach for question 4. See, whenever you have infinitely many solutions to be shown, which means that you have all the freedom to choose the sort of constraint the problem anyhow you want. And as a first step, let's try just changing the variables to something where this x minus y, y minus z are involved. The motivation for that is something like this. Unfortunately, when I was seeing the PDF, right, this was problem and solution was there. I didn't know that, so I didn't get a chance to try it without looking at the solution. But I would like to think that if I had attempted it, I would have not landed with the same idea. But I don't know. But yeah, just trying to remove myself from any bias, having looked at the solution. How can you start thinking about a problem like this? So So first thing we have to think about is that whenever you have like this problem having three variables, right? Classify whether it is a symmetric problem, not symmetric. So firstly, is it a symmetric problem in XYZ? Can we permute XYZ variables anyhow we want and still allow this to be valid? So you realize that it's not, right? Because if I swap two variables, right? If I swap X and Y, LHS will remain constant, but what will happen to the RHS? This will, the sign of this will reverse. This will become X minus Z, and this will become Z minus Y. So basically all three are getting reversed. So the whole sign is getting reversed. So we cannot swap two variables, so it's not symmetric. But do you see it is cyclic? So if I change X to Y, Y to Z, and Z to X, then everything will remain fine. So it is a cyclic polynomial expression. So when it is cyclic, what does that mean? That we are free to rotate XYZ in some way so that some condition can be met, such as X is the largest or X is the smallest, something like that. So without loss of generality, we can say, let's say Z is the smallest. And also one thing we notice, we cannot have any of them or other because we are free to choose X, Y, Z any we want. We will ensure none of these are zero. So it's like strict inequality. No two are equal. That is something we can enforce. Okay. So in that case, if Z is the smallest, then if you just look at the RHS, this Y minus N will be definitely positive. Z minus will be definitely negative. And so if the RHS has to be positive, what does that force?
X minus Y is negative.
X minus Y is also negative. So basically, just by assuming that Z is the smallest one, we can also conclude that X is less than Y. And so basically, that means that Y is also the greatest of all these, right? Because Y is greater than R. So we don't have to assume that as a without loss of generality, but it's coming as a conclusion of a equation. So now we can say that this is the order of the three variables. Z less than X less than Y. And there somehow that seems to me an idea that I want to look at the difference between these two and sort of change our frame of reference into those difference variables. So, okay. So let me call Y minus X as A and X minus Z as B because I would like to keep everything positive, right? So now I can choose any one of X, Y, Z and AB as my three new variables. So again, to keep things symmetric, the middle one, right? I would like to keep the middle one as the frame of reference, so that Y is X plus that and Z is something minus that. So I would like to write Z as X minus B from this and Y as X plus. Okay, so now the new system of equations will include X, B and T. So Y and Z will go away from the equation. So when I do that, what will my original expression start looking like? So LHS will become X square plus Y square will be expressed by X plus A whole square plus X minus B whole square is equal to, on the RHS it is AB into A plus B. And we have to show that this has infinitely many solutions possible. And now if you see, if you can just rearrange this and get a quadratic in X square, right? So I get 3x square plus something times X plus some constant. It will be 0. And if I want infinitely solutions of this, note that these expressions have only AB. So if I can find AB such that the discriminant of this is always going to be a perfect square, then I'm done, correct? So in particular, if you look at this particular term, it is actually A minus B, something times A minus, because here this will be plus 2xa and minus 2ab. So I mean that 2 will come out as a common term. But basically A minus B times X plus some other expression. This is going to be what I want. And so again, because I already seen the solution, I know that how to motivate this. Right. Why don't we try whether A and B are equal to each other? So what if A is equal to B? Okay, so if A is equal to B, right, then this middle term goes away completely. So then it's only the matter of showing that this part is 3 times some perfect square. So if we show that this part is 3 times some k square, then or rather minus 3. then it will mean that you will always find the value of x which will satisfy this. Okay, so this is the outline of the approach, but I will leave it as an exercise for you to complete the details. And at least this will lead you to one family of solutions, but doesn't be probably not the only family because there is a lot of freedom involved, but doesn't matter. If you find one infinite family, that means that we have infinite solution. Okay, so with that, I'm almost close to leaving. So let me conclude today's lecture on this. But like the overall strategy that we are looking at, so estimation is one important idea that we saw. They are given in this question 3, the going to the symmetric frame of reference, x plus y and xy. That is something you can think about. Whenever you have a cyclic expression, choosing one of them to be the smallest or the largest can help. So these are the common patterns that will be relevant for any other problem. Obviously, there are many more questions like this in the past paper. So again, depending on which difficulty level you are comfortable, you can solve RMO, INMO, or IMO shortcase problems. And as usual, you can always solve the questions and send them to me, and I can help you evaluate and give you some feedback. Okay. So I think that's all for today. By the way, I think next time we'll definitely discuss this question because there's some interesting. You see, it's a overlap between functional equations and number theory. So how do you combine those two ideas together? It's a very interesting. It's not a very difficult question, but it's still nice to attend. We'll do that next time. And then again, I will have to switch gears to something different. Maybe algebra or geometry. Let me decide for next time. So this is the pattern I'm going to try and do. In fact, I'll avoid geometry because as you already got the not invitation, but you must be added to the WhatsApp group, right? So for the training camp, it's going to be conducted in Pratishthan towards the end of this month. So I will be taking mostly geometry there. So let me not do geometry in our lecture. So I'll do something other than geometry in our session. Okay, I think that's all for now. Thank you. Bye.
Bye, sir.